So I'm going to talk today about two papers that we wrote this year that are along the same line of work. One, and they're getting at this main research question where we wanted to, everyone loves LSTMs, you need to use them, different kinds of RNNs are basically mandatory at this point, but they're not very interpretable. So our first project, we were really trying to come up with something that was a drop-in replacement for an RNN, but that was aiming for interpretability. And so as a side effect, it ended up being parallelizable, data efficient, and sort of well-behaved. I'll maybe go into more detail about what I mean by that later, but and at least for the task we tried it on, it was very competitive with LSTMs, which was sort of a surprise. So this is a job talk, so I'm going to talk a little bit about the graph-based semantic parsing work I've done earlier in my PhD, and then I'm going to get into these two papers. So the first one is work with Roy Schwartz and Noah called soft patterns, and that's our interpretable model that's a sequence encoder. And then I'm going to tease this EMNLP paper coming up called Rational Recurrences, where Hao Peng is the first author, and we explored the limits of what is possible with this approach. So first, just a little bit about my earlier work in my PhD. I've done a lot of stuff on graph-based semantic parsing. And by semantic parsing, I'm talking about parsing text into formal representations of its meaning, not necessarily executable against a database or anything like that. More broad coverage linguistic formalisms. So this is not really semantic, but this is a graph that we have parsed to. This is just syntax. So it's a tree, but I just wanted to point out that this is also a graph. This is a formalism I really like. We've done, I think, 4 papers on it at this point, called semantic dependency parsing. And this is a lot like syntactic dependency parsing, except that the labels on these dependencies are semantic relationships instead of syntactic relationships. And it's no longer a tree, because the same entity can participate in multiple events or situations in the meaning of a sentence. So for instance, soda can have 2 parents, and can have 3 parents. No, 2 parents. Whatever. So it requires a different set of techniques than syntactic parsing. We've done a lot of work on FrameNet also, some with SoPa right here. And it's not naturally a graph, but you can convert it into a graph. So this is a kind of semantic role labeling, but it has these nice rich frames instead of just verb senses that you're parsing to. We've done abstract meaning representation. We had the first AMR parser in 2014. Also a graph representation of a meaning. This time the nodes are more abstract. They aren't necessarily tethered to the tokens of a sentence, so that has its own set of challenges. Basically, if you can convert your formalism that you want to parse to into a graph, then I have good techniques to parse to it. And spoiler alert, you can convert your representation into a graph. Everything's a graph. Oh, here's another paper with Rowan, where this is called scene graph parsing, and this is not just detecting the objects in a visual scene, but also detecting the relationships between those objects. So some of them are just spatial relationships, a lot of them are, but some of them are more semantic relationships, like the woman is riding the motorcycle, etc. Okay, so that's a whirlwind tour of all of the graph-based parsing stuff I've done so far. Let's get into this new line of work. So this was done here in the beautiful Pacific Northwest with Roy Schwartz and Noah Smith. This is, the work is called soft patterns, or SoPa for short. And with this, we're really aiming for an interpretable RNN. So the task that we are going to try this on is text classification, just given a short document like a product review or a movie review, predict a binary positive or negative. This rock stories corpus is a funny one. It's basically a story close task where given a paragraph and two potential endings, you have to predict which ending is the real ending. And we just threw away the prefix of this and just treated it as a style transfer, following on some of Roy's earlier work. So ideally, you should get 50% accuracy on that if it were a good unbiased corpus. And just as an example, in Stanford Sentiment Tree Bank, these are fairly short, usually one-sentence reviews. Amazon product reviews are longer, but they're basically in the 1 to 2 sentence range for SST anyway. And so the inspiration for our model to make it interpretable was we went back to these things called Hurst patterns that come from the early 90s. And they started as handwritten little patterns or rules, like X such as Y, or X was founded in Y. And if you find something that matches this pattern in a corpus, then that tells you something about the spans of text that match X and Y. So for example, X such as Y tells you that X is a type of Y. And it's been used for a lot of different kinds of tasks, hypernymy detection, information extraction, document classification, text generation. And they were generally learned using statistical count, pointwise mutual information, and thresholds, sort of old-style statistical methods. So our idea was to take this general idea and maybe bring it into the modern end-to-end learning age. So they started as just fixed patterns, but some later work made them more extensible or flexible, where you can add or delete words into the pattern. Like, for example, funny, you could add in there without changing the meaning of the pattern, or you can drop the or you can maybe swap out one positive sentiment adjective with another positive sentiment adjective. But they're still hard match patterns. You either match this pattern or you don't. So that kind of flexibility of word insertion and deletion might evoke the idea of a regular expression or their operational counterpart, the finite-state automata. They're very easy to capture in this kind of framework where, you know, optional words, you put a little question mark, or in the FSA, you can use an epsilon transition. You can use, you can match multiple words on the same transition. You can use self loops to possibly insert adjectives or adverbs over and over again, et cetera, et cetera. So we started with this framework of an FSA with a sort of short fixed structure, and we decided instead of matching a single word along a given transition, yes or no, let's use a weighted variant and just do a soft match on that word. So now instead of yes or no, this transition matches this word, we look at the word vector and run it through a simple one-layer feed-forward net and get a score between 0 and 1. How well does this word match this transition? So each each transition now has its own parameterized little one-layer net that gives you a score. How well does that word match that transition? And we kept this very simple fixed structure of the FSA and let all of the learning be done by these little parameterized weight functions. So this is the basic structure of SoPa. If you're not familiar with reading FSAs, this little arrow into it tells you you start in this state. This tells you the function given the word, what's the weight. As you read through a text document, you start in the start state and you transition to new states with a weight corresponding to that weight function. So these first and last self loops are hard-coded to 1. That corresponds to basically letting you match this pattern anywhere in the document. Lets you sort of loop for free and start your match anywhere you want in the document and end anywhere you want in the document. And these self loops in the middle let you insert words like funny or whatever. But now now it's learned which words you're going to be able to insert there. So that's the basic structure of this model. You can also look at an FSA or a weighted FSA as a transition matrix. So this is just a different way of picturing that same FSA before. This tells you the transition from the first to the second state. So all of the self loops are on the diagonal. All of the forward 1 transitions are 1 off the diagonal. And then if you want to score how well this pattern matches a given document, I glossed over this before, but each state has a start weight assigned to it. So you can put that in a vector of start weights. Each state has an end weight assigned to it. So you can store that in a vector. And then the forward algorithm is, you can just write it like this, where you compute a matrix for each word, the transition matrix. This is a square matrix that tells you how to get from one state to another. And it's just vector matrix multiplication all the way across. So this tells you, if these are probabilities, it tells you the probability of starting in a start state and taking any path into an end state. So each one little FSA like this will give you one number or one weight for a document at the end. So what we did was we stacked 200 of these little FSAs into an array, each with anywhere between 2 and 6 states, but with this same fixed linear structure. And then each one scores the document in parallel. And then at the end, you get a 200-dimensional vector that's a kind of encoding of that document. And then to classify that document, you feed that into a multi-layer perceptron. So this is the fact that I wrote this as a function of the word, but really we're looking up the word vector. So this really is a drop-in replacement for an LSTM because it takes a sequence of word vectors and it returns one vector at the end, or you can think of every prefix of this function as the hidden state at that time step. And so this is an illustration of just two little patterns matching a short document. And the nice thing about this is that because it's little WFSAs, you can actually inspect these activations as you're going through the document, and they make a little bit of sense. So for example, you can tell that this blue pattern is matching on fieldings to go from the first to second state and to go from the second to third state, and then it's using a self loop to match on most, and then a forward transition and a forward transition, and then that is the span that contributed to the final score. So this is easy for me to read because I've worked on this for a year, but you can imagine that this is at least a little more interpretable than LSTMs, that these activations actually have semantic significance. So we ran these experiments on the Rockstory, SST, Amazon, and we used the same general setup for a bunch of different baselines where you run a sequence encoder, like a CNN, an LSTM, a deep averaging network, or hard patterns. So these are the old style heuristically extracted yes or no, we match this pattern. Deep averaging networks are just, you take every word vector, average them, and then run that through an MLP. By LSTM, you run it over the sentence, feed that into an MLP. Convolutional networks, these are just fixed length neural feature extractors. So the whole architecture is generally the same, and we just swapped out that bottom layer for all of these experiments. So you can see that for these smaller corpora, we're doing quite well in performance. Rock and SST are both about 5,000 training examples each. Amazon is about 100,000 training examples, I think. So even in that larger data regime, we're pretty competitive with LSTMs, and we're using much fewer parameters. This parenthesized number is the number of parameters in the final tuned model.
So is this the Rockstory task itself of predicting the ending of the story?
This is our, or Roy's simplified version of Rockstory, where you throw away the beginning of the story, and you only look at the two possible endings, so it's more of a style detection thing.
Where do the patterns come in?
They are learned end-to-end, just as in the other tasks. They're just, they're learned from the data.
And then the hard?
Yeah, these are the old-style flexible patterns that are they're extracted using pointwise mutual information and threshold kind of statistics. Yeah.
So you're trying to find patterns that distinguish the correct.
Yeah, exactly. And then they're fed into an MLP also. So this, that gets the worst performance usually, though not laughably bad. Maybe in Stanford it's pretty bad, but yeah, the rest of the 4 models are all learned end-to-end. Yeah.
Do you think the different models, especially CNNs and LSTMs, provide a different representation? Do you think you can benefit from both representations, or do you think SoPa kind of makes you avail the need to have the older representation?
Well, if you're going for maximum performance, then you probably want to use whatever performs best. If you stay only with SoPa, then it remains totally interpretable. You can explain the model's decisions without any sort of approximation or anything. You can really look and see the model made this decision because of this word choice right here. And I'll go into that a little bit more. And you lose that if you add in more side channel information. So we can dive in a little more on the model's performance on small data. So this we just artificially limited ourselves to smaller training data and ran the model and saw how it did. So this brown line is the hard patterns that are doing terrible on Stanford. The rest of them are all fairly similar, but you can definitely see towards the left side of this graph that there's some daylight there where SoPa is doing significantly better with less data. And these are all, we retuned the hyperparameters for every different training size, so it was definitely a fair comparison. And feel free to ask questions, interrupt me. I think I made this short enough that we'll have plenty of time. So I claimed before that this was interpretable. I don't know if that model picture was the most convincing argument, but here is, I think, something that's a little more convincing. So you can look at the model's decision on any one given test instance and see exactly why the model made its decision. So to do this, we're using Viterbi inference instead of the forward algorithm. So this is basically like max pooling instead of sum pooling all of these patterns. And when you do that, you really get one specific span per pattern that pattern picked up on in that document. And you can do an analysis of how much that pattern affected the final prediction store in the positive or negative direction, and then highlight the most important patterns in that document. So that's what we did for these few examples out of, I think this is out of the Stanford sentiment tree bank. So these bold green patterns are positive sentiment spans that a certain pattern matched on. So all of these different spans in the same document are matched by different patterns, but I'm just highlighting the positive and the negative ones. The orange italic ones are negative sentiment. So I should also point out that you can do this same kind of analysis with a CNN, with a convnet. You'll just get fixed length spans in that case. So you could think of this as an extension of convnets that allow, because of these self loops, gappy spans. Yeah?
So the polarity comes from the weights that multiply the corresponding index?
Right. So if you just fed this into a linear layer after to do your prediction, then you could just read off the weights. Since we did a 2-layer MLP afterwards, it's a little more complicated to see the effect, but we did that by keeping all of the activations fixed and zeroing out one pattern and seeing how that changed the prediction.
So I don't know if now's the right time to ask, but it seems one really interesting thing about interpretability would be to look at the places where it's making errors in prediction and then use those to suggest either improvements or at least what are the limitations of the algorithm. So are you going to talk about that at all?
We don't have an error analysis of the final model. We did use that during the development of the model. I know at one point while we were developing this model, we were seeing that every pattern was matching on the whole document, which was not the effect that we intended. So we used that to go in and say, oh, we should probably have a sigmoid on those self loops. And that helped us sort of bias the model in the direction we wanted. But no, we didn't do a full error analysis, unfortunately.
I have a question trying to understand how this relates to any neural network that has some memory. So in an FSA, if you want to have more and more memory, just make the states more fine granular, right? The power set or something, you can capture all the context and things like that. So what knobs do you have here to determine how much the memory do you want the state?
Yeah. So that's a really good question. I think the second half of my talk is going to to get into that question a little more. But yeah, that's a super interesting question, and it's more or less what we were trying to ask and answer in this rational recurrence second half.
So the classical pattern matching methods, they were based on writing patterns for the positive class, right? Do you see that the patterns you discover, some of them are high precision for the positive class and some of them are?
Yes, absolutely. So you can sort of get a sense already just from this visualization that there's about maybe a little more positive sentiment patterns, but there are almost half negative sentiment patterns. And I don't think we looked at the exact percentages of positive versus negative, but I believe it was about half and half.
Are you controlling the number of patterns that you generate, or is that?
Yeah, so that was a hyperparameter. We treated that like a hyperparameter, both the length of the patterns and the number. So, you know, we tried all different kinds of mixes.
How sensitive is the system to those parameters?
I don't have a slide for that. It was, one thing we found was that after 200 patterns, you weren't really getting much after that. But you know, a dozen patterns was definitely not enough. And our final model had a mix of 2 all the way up to 6, I believe, patterns. So it wasn't all getting done just by the short patterns, we know that much. And it wasn't just using the longer patterns was not the right thing to do either. It was a mix. So here's a different way you could look at what the model has learned rather than looking at individual decisions on a document, looking at one pattern out of the model, running that pattern over the whole training corpus, say, and seeing which spans of text that pattern matched in the training corpus. So these are taking one pattern here, and these are the top 5 matching spans in the training corpus. And with FSAs, you can do backtraces, so we know that the way, for example, this second span was matched was by using a self-loop on this scaling thing. So you can sort of line up these text spans in columns and see exactly what each slot of the pattern is doing. And they're moderately coherent. So, you know, a lot of, this one's very coherent. It always matches commas. The first slot is matching positive sentiment adjectives. Apparently, ands and commas are very similar functionally. But so this is all learned from data, and happily, this kind of at least semi-coherent pattern kind of fell out of the data. And here's another one. This was another funny artifact that we found when we looked at what the model had learned. We had epsilon transitions, sort of glossed over them earlier, but these allow you to skip states without consuming a word. They didn't end up being used very effectively. They ended up being used for this purpose, we think, which is just to shorten the pattern, to take a 5-length pattern and turn it into a 4-length pattern. So self-loops ended up being used a little bit, and they helped, and epsilon transitions ended up not being so useful, especially since we're already tuning that hyperparameter. So that, yeah.
So it seems one advantage of using bi-LSTMs would be that you can still use them for, let's say, span predictions at each token. Do you know if this can also be applied there, or is it more for a text classification?
Yeah. So text classification was sort of the simplest task we could think of to test this out. In the rational recurrences paper, I'm not going to talk about the experiments much, but we do language modeling. So we do use it in that way. And basically what you do is you just run it over the prefix. So that that computation so far is your representation after John. That computation so far is your representation after Sa, etc. So you think of it as just running it over the whole span that is a prefix of the left context. You could do it with the right context. Yeah.
So without self loops and without epsilon transitions, does it become like equivalent to matching frequent n-grams?
It's definitely fixed length n-gram. Each pattern has a fixed length, and it will match fixed length n-grams. It'll be, since it's each transition is a neural function of the word, it won't be exactly n-grams, but it will have n slots that will match the different parts of an n-gram. Yeah. So a lot like a convolutional neural net, which I will get to. So I just wanted to first introduce Hao, who we recruited to lead this next section of the paper, or the next paper. So he's going to be presenting this at EMNLP if you're going to be there in the language modeling track. So I just want to at least tease this work a little bit because I think it's really cool. So in this project, we, instead of looking at a specific model that we designed to be interpretable, we asked that question of, well, what can you do with WFSAs? It seems to be more than previously thought. What are the limits of this general approach of learning a bunch of little WFSAs with neural weights end to end? So we carved out a little complexity class that already exists that we call rational recurrences. And this rational comes from the old WFSA literature. It's the analog of regular in unweighted FSAs. So the same way regular expressions, regular languages. The weighted analogs are rational series. Rational kernels were things that were worked on in the 90s. So here's the definition. A recurrent network is rational if and only if its hidden state can be calculated by an array of FSAs over some semi-ring. And I'm not going to go into too much detail, or really any detail about what semi-rings are, but if you're familiar, you can swap out the plus and the times operations when you're doing this forward algorithm, as long as you follow some laws. And it's a nice flexible thing you can do. And since semi-rings are pretty flexible, we put this little asterisk there where the operations have to take constant time and space. So when we're going from unweighted FSAs to weighted FSAs, a lot of the intuitions about expressive power don't really hold anymore. So a lot of people are well aware that you can't parse HTML with a regular expression. For example, this is a famous Stack Overflow answer where the user is getting more and more frustrated as they explain this. You can't parse HTML with a regex. But when you add weights, you're adding expressive power. So now you have two places where you can store memory to get to your earlier question. You can store it in the in which state you're currently in, but you can also store it in the weight itself. So here's just a simple little toy FSA, WFSA, that just remembers where in the document you saw the word the. So it's going to match with a 1 if you see the word the in this transition, 0 otherwise, and then it's going to decay by 1/2 as you get farther. So this, if you run this FSA, it's going to give you a binary decimal encoding of everywhere in the document that you saw the. So this is definitely not something you can do with an unweighted FSA. So if you have one of these for each word in your vocab, say, you could just totally memorize the whole document. And semirings can be structured. You could do this even easier if you use a semiring that basically just remembers the input as a list. So I think to get at your earlier question, one thing that you can do with an FSA is simulate a one-layer linear convnet. And all you have to do is take SoPa, take away these self-loops in the middle that allowed gaps. So we're no longer allowing gaps in the patterns. And we took away the sigmoid in this transition function. And we're using Viterbi inference instead of forward algorithm. So if you run this FSA, you're going to get a max pooled one-layer convnet. You cannot do more than one layer at a time, but it's sort of cool that this is a special case of this class of models. And another model is the simple recurrent unit. And there's actually two more models that are almost exactly like this in our paper. But this is a really sort of simplified RNN that has a content layer and a forget gate, basically. So you can get the intuition here that this main transition is matching the content layer, just sort of a unigram feature of any given word. And then this self-loop at the end is like a forget gate that decays the weight of that feature match as you go. So this is just one component, one dimension of an SRU. But it's sort of nice that you can get this intuition about forget gates and content layers and how they correspond to FSAs. And one thing that I think is interesting is that the forward algorithm is directionless in a way. It's just a bunch of matrix multiplication. So you can calculate it right to left, left to right, however you want. The only thing that's really giving this its direction is that this self-loop at the end is less than 1, and this one here is 1. So that's getting you the recency bias. And you could just switch that if you want to do, and it would give you whatever the opposite of a recency bias is. Here's another example of a model that's already out there. It's called the input switched affine network. This model is basically, you take a hidden state vector and you do an affine transformation of it that is keyed on the current word to get the next state. And so this can be, if it was just a linear transformation and not affine, it would really just be an FSA in the old style days. So the only little complication is adding in this bias vector, and you can do that with this clever little way where you add a state for each state that its whole job is just to refresh itself as you go through the document and add in a bias term. So we have, these are just two examples. We have a bunch more examples of recent, or mostly recent, recurrent neural networks that we show are actually WFSAs in disguise. So in a way, we're stealing all of their experimental results. You can, quasi-recurrent neural nets especially get really strong results. And since we're showing that they are WFSAs, we're showing that you can get very strong results with this kind of WFSA.
So this reduction is, the point of the reduction is to show that they're rational
Mm-hmm.
RNNs. Like, I thought that you removed the nonlinearity, which we know is important for getting good performance with any of these models.
Yeah, well, we've basically shoved all of the nonlinearity inside this T matrix. Where'd I go? So you can use whatever nonlinearity you want to fill out the entries of this T matrix. But then once you've done that, you have to use matrix multiplication to do the calculation after that, or some other semi-ring. So we've basically limited where you can throw in the nonlinearities. But this is, I mean, it does restrict the model. Like, we didn't prove this, but I'm 99.9% sure that LSTMs are not rational. Elman networks are not rational. Recurrent additive networks are not rational. There's a lot of things that are not rational. And we threw in that asterisk just to really be sure. That you're not.
In terms of the practical implications of this finding, what can we do now that we know that these certain model types are rational?
Well, so some of these newer networks were already designed to be efficiently calculatable, like quasi-recurrent and simple recurrent units. Part of their whole selling point was that you can calculate them in parallel. If these other ones didn't already know that, now we know that they are efficiently calculatable. Left to right, right to left, divide and conquer, lots of different calculation strategies that you can use now that it's all associative. It gives us some intuition about forget gates versus content layers, what these different parts of the model are doing. And so I didn't include the experimental results of the rational recurrences because I didn't want to steal all of Howe's thunder. But we do use these kinds of insights to design new models that are sort of simple extensions of what we've already done in different ways that this FSA view leads naturally to. We get very strong results on language modeling and text classification, even stronger than the SoPa results.
Two questions, Captain. The first one is what you mentioned about stealing other people's results.
Yeah.
Actually, I wonder if it's more subtle, because I know when you say knowledge-based computation, two methods can be equivalent in the Fourier transform, but they don't train as well with stochastic gradient. So one could be more trainable than the other in practice.
Yeah, so that's a good point. I think all of our constructions, except maybe the quasi-recurrent RNN, most of our constructions are very direct translations of how the models already work. So the training would look almost exactly the same. I don't think we would mess up training there. But yeah, that's an interesting question. I can't think of any other way that would affect training, but that would be interesting to think about, yeah.
The second is the word rational. Is that supposed to involve like rational behavior rational?
No.
Rational numbers rational?
There may be some kind of indirect connection to rational numbers, but that's not where it came from. It came from the mathematical literature about the same way that regular expressions are equivalent to finite-state automata. Weighted finite-state automata are equivalent to rational series or rational power series. So that's taken from the math literature. And it's not directly connected to rational numbers, I don't think. So I alluded to this already, I think, but because this is just matrix multiplication, it's all very vectorizable. You can throw it on a GPU or a TPU even. You can map reduce it. It's directionless. You could have a mix of putting that forget gate at the end on some patterns and put it at the beginning on some other patterns and sort of calculate both directions all at the same time if you wanted. There are a lot of semi-rings out there, so we don't really know the full extent to what you can do with this. One thing I'm currently working on and extending this to do is to use this for graph encoding. So a nice thing about FSAs is that you can asterate them. So instead of encoding fixed length sequences, you can encode all the paths in a graph, even loopy paths. So hopefully that'll finish up soon enough, and I'll be able to talk more about that later. And all of this is free and open source, released on GitHub. So check it out, play with it if you want. Thank you.